The world is full of so much data, and collecting, refining, transforming, and analyzing it becomes a bigger challenge every day. Like a frog slowly boiling in a pot of water, it all just slowly creeps up on you until you just can't manage it anymore. You might be surprised to find that you are suddenly thrust into the world of HPC. So today, we're going to be talking with a well-known HPC expert, so stay tuned. Hey everybody, this is Chris Brandt here with Sandesh Patel. Welcome to another FUTRTech video podcast. One big trend I am starting to see is more and more companies stepping into the big data world with hyperscale and high-performance computing environments. This is a world where one size doesn't fit all, and these environments tend to be more like custom hot rods than traditional computing environments. Today, we're talking with HPC expert Ryan Quick. Ryan built HPC environments for eBay and PayPal, and now operates his own consultancy to help companies navigate the complexities of these builds. Ryan is going to tell us about what HPC is, what it takes to build, and why you might want to start now. Welcome, Ryan.
Hi, how's it going? It's good to be here.
Thanks so much for being on and with the extra special guest. We always
you can see her. I can't see her. I couldn't tell if you made it in frame or not. Hey, little one, I have to go. I have to do some talking for a little while. So can you go sit? Okay. Yeah. I'm super glad to be here.
So Ryan, well, thanks so much for coming on, and tell me a little bit about what HPC is.
So, it's obviously it stands for high performance computing, which is kind of a misnomer, because what it really is I think you're tuning your problem and the computer at the same time, so that you are really, you're solving that particular problem with a combined unit. Whereas, we're used to sort of taking basic capabilities, putting them inside a box, and then we know what you have this much RAM and this much CPU available and these kind of disks, and then you can work on your workload. With HPC, generally the problem already won't fit in that normal box, but at the very large scale, you're building these supercomputers that are designed specifically to work on certain types of problems. What people don't realize is that supercomputers, while they're extremely powerful, are often can be terrible at a different type of problem than the one that they were designed for. And we saw that a lot sort of in the early 2000s when HPC sort of came out of the DoD and became sort of more mainstream the first time. A lot of people tried to do big data problems with them when you started to have things like the Hadoop wave and stuff like that. A lot of those systems weren't designed for that type of computing, and so trying to push them into that, even though they were gigantic, they weren't very good at it. And you could solve a lot of those problems in the sort of the big data era. You could solve those on smaller clustered machines differently. And that also confuses people sometimes in that, grid computing is one type of clustered computing. Kubernetes today with container orchestration and things like that is another type of computing, but both of those tend to be distributed computing problems, which is sort of the domain of hyperscale. HPC is, generally speaking, parallel computing. So you usually have one master computer made up of however many nodes, but it's generally working on one problem at a time with all of the nodes, and that's kind of a difference. Now, we can debate, and we probably will throughout the rest of this, as to whether or not that's always a good idea, but that's sort of the general general idea between HPC is you're tuning the computer to the job. It tends to be parallel computing, and your computer is now not general purpose anymore, and you have to keep that in mind.
Well, and I've heard you say, before that HPC is not necessarily high tech as well. Could you talk about that a little bit?
Well, HPC tends to be high tech in the hardware side, but that doesn't necessarily mean that you're modern tech or high tech in how you're using the computer side. In fact, most of the time, especially for very large computers in academic centers and government centers, the software that you're running on that platform is actually very old. It's almost, it's probably heavily weighted, if not the majority. It's still close to the majority. Written in Fortran, which we don't use very often at all anymore. Yeah, you see, you're already laughing.
No.
It's okay.
Where do you find people to do Fortran?
HPC people, they all know Fortran.
Yeah.
And they will swear by it, because they'll sit there and go, when I say an I is equal to 1, it is equal to 1. That's like the big, that's the Fortran, right? Yeah, so a lot of those codes, can be 20, 30, 40 years old. And they can be millions of lines of procedural Fortran, which it's a nightmare. You don't see modern functional languages very often at all in the HPC world. That's starting to change as AI and machine learning start to come, to bring themselves to bear and start to have some of the same problems. You're starting to see some of those citizens in the city, so to speak, but yeah, a lot of times you're seeing old stuff. So yeah, absolutely. Just because it's high tech on the hardware side, and they generally are, doesn't mean at all that you're running modern technology from a software or a systems administrative side, and that can cause problems because well, we all know how computer people are, right? If there's a group that can be said to have a gigantic chip on their shoulder, it's computer guys, right? And so one of the things that HPC is sort of notorious for is that they have that high tech chip on their shoulder, but I'll tell you right now that they don't earn their stripes when it comes to managing the systems. That is wholly owned by the hyperscale guys right now.
We hear a lot more about HPC and hyperscale. I mean, I think a lot of these technologies are really bubbling to the surface because the problems that people are trying to solve are getting bigger. We're dealing with much larger amounts of data, much larger systems, bigger problems. It's becoming harder to wrap our compute around some of the problems we're trying to solve. I mean, what are you seeing? What is it that is making HPC so relevant these days?
I think it's that the first part that now the problem's gotten too big. So one question I get all the time is sort of, why HPC? What has to be happening in the world for me to go, holy crud, get HPC, right? And
what's broken in your life that you need HPC?
What is it? And what I usually say to that is, well, if you're asking that question, you already have the problem. But most of the time, it's because the shoe doesn't feel right anymore. You're trying to do things that you can, your programmers are looking at you askance, like, you sure that we want to do that? Or I don't know if this language can handle that. Or, every time, 6 out of 10 times when I run it, the computer crashes trying to do this kind of job. That's the type of stuff that starts to put you into the HPC world. The other types of things tend to be more scientific in nature. So if you're, the data sets have gotten bigger. In fact, your intro kind of alluded that we're in this sort of era of big data. But what goes along with that to make it an HPC problem instead of a big data problem is that your data has gotten big and the breadth of your question has gotten wider, but the time to answer has either stayed the same or shrunk, so that you're having to do more in less time than you had before. And so, with software, you can do big, amazing things as long as you don't care how long they take. But as soon as you want to start measuring things like latency and stuff like that, now the only thing you can do is either not do it at all, which is a latency of 0, or have faster hardware. But being able to write software to take advantage of the faster hardware is difficult. Like on laptops and small mini computers, they've been using NVMe M2s for a long time now, right? Probably 5-6 years or whatever. And they're now catching on to the desktop world. But no one's running desktop operating systems that can really make use of how fast an actual NVMe can really be, right? And so, but in the HPC world, there's all kinds of code that bypasses everything else in the operating system just to use the NVMe bus or to create fabrics out of the NVMe. These are the kinds of things that HPC will do because they need that extra, that latency matters. The 4 nanoseconds they get back by bypassing, this level of code in the operating system is definitely important to them. And that's the kind of stuff that'll start to happen when you need it.
When we talk about, there's a lot of components to this, right? Or maybe there isn't as many components as I think there is, right? The high tech versus, all that. But when you say, what are the components that go into an HPC environment, and like what kind of skill sets do you need?
The components aren't any different than what you would normally associate with compute. They need compute. CPU power, they need memory, and then they need network bandwidth, and then storage. Now, and a lot of times with HPC, network and storage get combined together, because that's generally an optimization they tend to make, so that the bandwidth, you want to make sure that you're getting the absolute most bandwidth to the storage as you possibly can. So the storage and your memory requirements tend to dictate how fast your network is, and so you'll find extremely fast alternate network topologies a lot of times in HPC. InfiniBand is rules the roost right now, but you also have technologies like Cray Slingshot, and even Ethernet to some degree that are popular as well, but they tend to be configured differently than you would see in sort of data center structures with different types of switch topologies and things like that. But what they do with those dimensions is where it starts to change into a supercomputer. So you may see what we would consider in sort of the general purpose world a wildly unbalanced system. So for example, in some of the large supercomputers, they might have 6 GPUs, high bandwidth memory with 2.5 terabytes in a single node, and only 2 terabytes of actual physical storage in the node. Something like that, right? Where we'd be like, right. But wait, what? You've got more memory than you have actual physical disk? Or like the last supercomputer that I operated, when I was working for PayPal, we didn't even have physical disks, right? Because our problems were compute and memory bound. So I didn't waste time putting physical drives into systems at all. I booted them off the network all the time, right? But I didn't use something like NFS, which you might see other places. I built a RAM file system and put the entire operating system into memory and ran that way, right? So it's a little bit different as to how you tune things, but it's the same dimensions that you would always do. They will tend to have more memory than you would, and they will always tend to have the fastest processor you can actually acquire at the time. So, if you've heard about it, you won't be able to buy it for 3 years because the first 2.5 years are all bought by the Hyperscale guys, and the HPC guys have bought the entire stock. You won't ever see it in real life for a long time. But yeah, there's no additional dimensions there. Sometimes there's, from a software perspective, there tends to be a work scheduler that's associated with the system. I kind of mentioned that this is where I divert and can sometimes be considered sort of an HPC rogue to some extent, because I'm not a big fan of the batch scheduling concept, but it tends to be there. I prefer more modern approach like container orchestration and things like that to be able to run those. But generally, there's your system has the computer, and then it has some sort of scheduler that allows folks to kick workload off on it. It doesn't often run like there's not a lot of daemon processes that sit out there and run forever, and there's not always a lot of client server applications. Most of them sort of tend to be self-contained, but that's that parallel computing thing again, right? You don't have a lot of nodes that are doing different work.
And you bring up an interesting point, because I think, when we look at whether it's just scale in terms of just pure capacity or just, power or speed, when you get to large scale, sometimes the problems flip themselves on their head, right? You get very counterintuitive things. And I remember way back when, in the early days of Google, when they released that one paper where they talked about how they had switched from using hard drives in computers to just using RAM, because it was actually more economical, because they could process the requests a lot faster by having it in RAM. Therefore, they needed fewer computers, and that way, even though they were spending more on the RAM, it was actually more cost effective to do it that way, right?
Yeah. And by the
so
time
I imagine you get a lot of that.
Yeah, when you factor in mean time between failure, drives always fail, and memory fails a lot less often. Yeah, it does make a difference.
So what kind of really counterintuitive things would you say that you see in your world that people would not necessarily always expect?
I think probably the one that comes up the most often is when the solution is larger than the problem. A lot of times, we have this notion, I think it comes from watching, like cop shows and stuff like that you start with a big problem and you want to zero in on the solution. And HPC is certainly trying to do that same thing, but a lot of times at least the intermediate steps, if not all the steps, will result in larger data sets and more questions and more work to do than you started with. And that can be actually that's a good signal for if you have a problem that's doing that to you, then you may have an HPC type problem. But that's the one I think I see the most, is where the problem gets harder the longer you work on it. Weather is like that, right? You would think that, you know, if I want to predict the weather in a zip code, that's easier than predicting the weather than, on, over top of 12 zip codes at once or whatever. But that's actually not the case, because when you're predicting over 12 zip codes, your resolution might be measured in 1.5 mile increments or whatever. But when you're predicting in a zip code, it might be measured in 500 meters. So the actual amount of data that you're looking at is quite a bit more. And because there's so much more variation in the smaller sets, it's more difficult for the computer to predict the to predict the answer. But at any rate, the other one that I think that might turn things on their head sometimes is that a lot of times CPUs nowadays have become necessary only to get the computer running. That most of the workload has now been moved to general purpose GPUs. They call it GPGPUs, which are a different animal to write code for sure. But if you understand how to categorize your problem in the types of ways that GPUs work for, then they do make quite a big difference. But yeah, it definitely puts you into a different category of software writing that, they're massively parallel. And so you have to think of your program in that way. Yeah, so there's a few types of exotic hardware that do show up more often than I think they do in other places. For example, FPGAs are relatively common in HPC world, but they're usually put to a particular task. And so understanding where an FPGA makes a difference and the way that it actually functions requires a much greater skill with computer hardware engineering than I think most of the time you got to. So, like a minute ago, you asked me skill set, and I'm kind of working my way around to it. But as a good general approach to answering, what kinds of skills do you need in order to be able to be in an HPC world? You definitely need folks on staff that know the hardware, right? Not just the hardware you bought, because good operators that can read the manuals for what you bought will understand the hardware that you purchased. But you actually have to understand how hardware interacts with other components to be able to find bottlenecks, to be able to understand problems. Because once you've got a computer that is just yours, this is no longer a Dell 1U or whatever. It is your computer built your way for your problem. Now you're the only person in the world that can fix it when it breaks, or even understand what's wrong with it when it's broken, right? Yeah. And so, you can't just get Dell on the phone, because Dell's going to see it and say, I'm picking on Dell. I don't mean to, they're D's and it came to mind. Anyway, if you get them on the phone, they're going to look at it and they're going to go, well, we ran our diagnostics on all our components and they seem to be okay. But your problem's still not working right. This is where you have to come in and say, okay, well, here's how I'm actually using this computer, right? 90% of the time it is using all of the memory, none of the disk. The CPUs are at this, the GPUs are this hot, and I've actually had this happen before. It's like, oh, you know what? When we go and analyze it, nothing's happening because people are taking it offline to go and look at the problem. They go in and take all the measurements. What they didn't realize is that when it was running, it was too close to the storage array. Storage array was exhausting and had hit some baffle that made some of the air circulate back around the front. And so the first 2 racks of nodes had 3 degrees different incoming air take than the others. And that was enough to skew the workload over the course of a couple of hours, that these nodes were getting too hot. And so it all came down to, having to adjust the airflow a little bit in the data center. But, that's something that Dell can't help you with, right? They don't know that, when you kick it off, this is what's going on, that the drives are all spinning at the same time that these first 2 racks of nodes are, because they're moving all this data at once. And that's enough to tip it over the edge. And so, it gets to be real weird. But yeah, you need people that know hardware engineering. At the very least, you've got to have, if you're not already running your own storage, that's probably the line, right? If you're relying on someone else to manage your storage for you, or you bought, sort of a self-contained storage array and you're just happy with it, it's probably not not right for you yet. But if you've got folks in house that are, managing, configuring your storage across the enterprise, then you probably got the right set of folks to get started. Storage is usually the first thing that people in-source, when they have, that's usually the first one where they bring in an expert. Not to say that network guys are always there, but the network guys generally are focused on the behavior of the network as a whole, not necessarily how the network interacts within the bounds of a single computer. And a lot of times in the HPC world, when you purchase an HPC system, the network guys are like, they just sort of build a wall around it and let the network of the system do its own thing. But storage usually still has to interact, because most of the time you have to get the information you're putting on the storage from somewhere else. Generally, it's not made up by the computer, and so it has to interact with the rest of the data center to some extent. So that's why I say storage is sort of the first spot. Well,
it sounds like what you're describing is project that never ends. I mean, it sounds like, the way you describe it is that, it's not a build it and forget it kind of scenario. It's a build it and tweak it and tweak it and tweak it and tweak it.
And you generally, because you're also spending a lot of money on a single computer, it'll probably be for most folks the first time that they're ever running a multi-generational single system. Right. Because, even if you go out today and you were to buy, sort of a grid, you would probably order a rack or two of the same thing and then call it a day. And then when your grid was failing or starting to get old, you would go and get another grid and then migrate to it or something like that. But with a supercomputer made up of, say, 20 racks on its own, you may want to depreciate that over 3 years, but you also may have your problem set growing over 3 years. So now you've got to make this computer bigger with different components than you started with. And how does that work, and how does that affect your workload? So now you're back into the code going, well, we can run these components on these two racks and this component over here, but they have to tie back together. It's a never ending.
It sounds like if you're worried about the airflow, like slight differentials in the airflow around components, that adding completely different generation pieces could really make it tough.
I call it Formula One of computing. It's if for systems administration and system architects, HPC is definitely the Formula One of the computing world, because it's always changing. The rules change every day. Your computer and your car is the only one like it in the world, and the guys that build it and race it every day are the ones that know it best. It's a good analogy.
You mentioned like FPGAs, for example, field programmable gate arrays, right? Which, could you describe what that is so that people understand like what kind of skill level you would need to bring in for something like that?
Sure. FPGAs have been around a really long time, and they are basically, well, their name says field programmable gate array. So if you didn't know, a processor is a series of gates. It moves electricity and flips things on or off, right? And a combination of ons and off make the particular instruction that you're issuing to the processor do its thing, whatever that instruction is supposed to. So a field programmable gate array is an empty processor with no instructions programmed into it yet. And so what you do is you write very low level particular types of software that are then literally burned into the actual device, so that now you have a piece of hardware that is running your software. Not exactly the same way that you do an ASIC, but they're close. So an ASIC is designing a chip or a series of chips that will function electrically to solve a certain problem. FPGAs are similar to that, but they can be reconfigured in real time with software. To program them, though, you're not programming in C or C is the lowest level there might be a driver for out there. You're usually programming in languages called Verilog or VHDL, and what those do is they compile directly to assembly, and then you're basically telling with Verilog where you want the different components of the assembler code to live on the gate array, and then gates. The other thing that's weird about them is that they're programmed in procedural ways, as if you were writing a shell script. That's the easiest way. The easiest way to think of it is, I'm writing a shell script, comes in the top, does other thing. It's not object-oriented program. It's procedural.
Right.
But it's all it's all timed in terms of a clock cycle, right? So every time the clock moves on the processor. You know, if you have a 1 gigahertz, that's, you know, turning 1,000 times per second. You know, so every time the clock cycle goes, the FPGA does its magic one time. So what you have to do is figure out how many clock cycles does it take to store this much memory over here, and you know, it's very, it's not for the faint of heart.
Yeah, no, that sounds rather complex.
If you need an FPGA, you'll already have people that are used to it, because it's a weird class. HFT and HPC, those are the two people that buy all the and switches, right? Network switches and telco switches are built with FPGAs. That's the, you know, if you're building switches.
Well, I mean, it sounds like, you know, if you're going to try to build this team, you should start as soon as possible and make sure you have a lot of money.
I'd avoid it. And I mean, to be honest, it really would. So, and I don't, you know, there's always that running joke. What's the difference, you know, the difference between a CIO and a CTO? HPC is definitely the CTO world by a long shot. This is a computer that you build yourself and you keep on building for the rest of owning it. First, you cannot buy one. You can't walk out on the street and go, hey, I would like a supercomputer. There are vendors who will sell you a variety of configurations of supercomputer, but when you sit down with them to try and buy it, you're going to get a 3-week long interview about your problem and the software and all, you know, all these things I'm talking about. They're going to ask you about all that before they let you buy anything, right? And so if you can't answer those questions, they're going to basically say, you know, you should probably outsource this problem, or call, you know. So that's kind of you know, a bit of a difference. If you can avoid having to build a computer that is just yours and all the headache that comes with that, that's great. Now, on the flip side, because of the headache, for HPC especially, there is a, I guess, unique spot in the world that you can attain, right? So you can opt to try and build the largest publicly known computer in the world. Currently, I think I haven't even looked, but I think it's Riken in Japan is currently occupying the #1 spot. And then the #2 spot is Summit at Oak Ridge National Labs here in Tennessee. Yeah. And so, yeah, they every 6 months they publish the top 500 public computers in the world. So if you have a supercomputer, it's just yours. You can run HPCG and LinPack and see where you place on this list. You get nothing for placing high, other than to be able to say, yeah, you get bragging rights to say, you know, you've worked on the biggest computer, and it does work. You know, my company has done some work on Summit when Summit was #1, and before they got displaced. And yeah, I did the same thing. I'm like, hey, we're here. This is the biggest supercomputer in the world right now. So, you know, they spend $200 million on a computer, and you get to say, hey, we're the fastest, until someone else builds one that's faster.
For about a week.
Yeah. Summit sat #1 for, I think, 2 years. They had 4 cycles before they got displaced. That's for them. For the top 10, they usually sit. They don't change very often in the top 10, and so those computers are built with a 3-year depreciation. They keep them longer than that, but they want them to sit where they sit for about 3 years. They call those leadership class computing, and it's that's like the super Formula 1 of computing. But you know, if you've got something that would place, you know, anywhere in the top 500, then you definitely have a bragging rights to having a very, very large computer. Most people will never see anything remotely like that.
You just need NASCAR, not the full Indianapolis 500.
They're all still unique. That's the biggest thing that's weird about HPC versus, you know, Hyperscale or anything else. You know, like Hyperscale is, you know, they're big and fast, but they're built with design patterns, right? You know, like, and so, you know, Facebook or somebody will have their patterns on how they're going to deploy computers, and then they'll go and buy a whole data center's worth, or, you know, Microsoft Azure or AWS or whatever. They have, you know, people who buy FPGAs. For both of those guys use a lot of FPGAs. And so, but when they do it, they're applying a design pattern to design large scale general purpose compute frameworks, right? Mm-hmm. Which is great, and I'm not trying to detract from that at all. That is fun and exciting computing, to be sure. But for HPC, it's you know, I've got this one problem. I need to know how wide the universe is between starting at that star and going over to that star, and I need to know the answer right now, and I need to be told every 20 minutes that that's the answer. so that's your baby. Whatever you end up
Yeah.
with that's solving that problem for you, it's yours, and it's only yours. And that's for hardware guys, that's cool stuff. It's just like, I have the only one of these in the world. But then, when you've woken up in the middle of the night, you're like, I have the only one.
I have the only one of these in the world.
Right? Yeah.
What is the most common use case that you're seeing in supercomputing? Is it more in like research? Is it more in the biosciences? Is it like in the financial markets?
Bitcoin mining.
I don't see too many supers doing crypto yet, but so there's definitely established sectors that have always had supercomputers, and those are not going anywhere soon. So that includes applied science, theoretical sciences. So physics is big. Cosmology is big, astrophysics, weather, life sciences, biosciences, all of those definitely have their known players. I think the ones that we're seeing the most of now is that AI is starting to creep in, right? You're seeing some very large neural networks that are being constructed. NVIDIA themselves, went, 4 years ago, they were providing a lot of GPUs, but they didn't have server offerings. Since that time, they now have, I think, the number 5 or 6 largest computer in the world under their own brand, and then they will actually, they're one of the few vendors you can actually go and buy supercomputers from, and so that's. They are changing, but the NVIDIA one is changing off of the shoulders of machine learning, AI, and I think to some extent biomed, but definitely AI and machine learning are the top two there. And if you go in and look at their computers, they're sold a little bit differently than the other guys. They come with a full suite of common scientific applications already installed, but containerized. Containerization is rare in the older stuff. Well, if you thought it was funny that I mentioned Fortran, can you imagine trying to containerize Fortran? It actually can be done, but talk about narrowing down the resume search.
Yeah.
And so I think that's probably the biggest ones. The other ones are, we're starting to see supers take over when big data clusters are now going through what would be their third uprev. So if you jumped on the Hadoop big data, map reduce wave early, you're now on your probably 4th to 6th generation of platform that you're using to do that. And the problem that those guys had was, while they had a decent solution for how to work that, it was a lockstep scaling unit, right? So you scaled your disk, your memory, and your CPU every time. So it was from a price perspective, it's a steady march up and to the right. So you have to make sure that your software is delivering more value than that increasing scale. And at some point, that's an infinitely, you're either going to run out of power or money or whichever. And so by the time you're on your 4th or 5th generation, now you're starting to hit that. Like you know what I mean? If you were on it early enough that was a problem for you and you've kept it, now you're spending a gazillion dollars doing that every year.
Right.
And when you start to have 1,000 node cluster for Hadoop, you've got 2 people on staff, I guarantee it, whose job is nothing but replacing hard drives every day. They'll come in the morning, they replace hard drives all day long. They go home, they come in the next morning, they replace hard drives all day long. That's all they do. I know, because we had several of those, and that's what those guys did.
Yeah.
And so, by the time you're at that generation, now you're going to start to say, look, is there a way we can do this more cost efficiently? Can we save some power? Can we solve these problems in a different way? And so you're starting to see tuning that particular big data model into supers and into customized systems to break the lockstep.
Yeah.
You still got the big data problem, but you're like, can I please scale any one of these dimensions separately so I can save some money somewhere?
Yeah. So Ryan, what's next on the HPC front? What are we looking forward to?
Continuing along that sort of merging of the disciplines thing. I think you'll see that more and more. AI, machine learning, neural networks will start to seep into places that they haven't traditionally been. That's been started for a couple years now, 3 years probably. That's not going to stop. I would really like it to start seeing people with answers. All these people are learning stuff. I would love it if we started to see more stuff. People going, look what I learned, and here's how I applied it. But that's a different topic for a different show. At any rate, but I think you'll still see a lot of that going on. What I think is probably the one that doesn't make the most sense, or that is kind of counterintuitive, or might be a little bit different than I think we'll start to see it is, I think the world of container orchestration and very large cloud providing will start to adopt HPC systems for the same way, because they're already on the verge of needing extremely tailored systems to do particular things, like consensus management in Kubernetes, which most Kubernetes users don't think about at all. But if you're operating large clusters, consensus is a big problem that you have. Well, it's not just a big problem. It's a memory bound problem, a compute bound problem, and it's reliant on small packets on networks, right?
Yeah.
That have to be delivered within certain latencies. And the bigger your network gets, the more you can do, but the latencies change, right? And for consensus especially, the more route hops you have, the more switch hops you have, the latencies are enough so that you're going to go into a new round of elections and you won't be able to make a decision. So you're trying to, you'll see them start to go with these, like, I want a 256 radix switch just to put etcd on, right? Which I'm telling you, you'll see it, right? And so I think that's probably one of the places that we'll start to see people borrow from HPC. They may not call it that right away, but I think we'll start to see Kubernetes with Dragonfly topology, or all-to-all Taurus 4D Taurus mesh networks being used inside Google Cloud for migrating VM memory, stuff like that. These very specific applications that have to do with large-scale distributed computing consensus at the core, and with particular data movement where the chunk size of the data is not something that can be optimized for standard storage. InfiniBand's great if you're moving a lot of data because it's got 64K packet size. It's perfect, right? You want to move big chunks of data, InfiniBand's awesome. But what you want to do is instead to move 64 million packets in a second. Neither Ethernet nor InfiniBand are particularly good at that particular problem. So it doesn't matter if you got 400 gigabits of bandwidth. You may only need 1 gigabit worth of bandwidth, but you're trying to do it with, more packets than a director level can handle, right? That's the kind of problem that you start to get in with HPC. And so, I'm putting my stake in the ground here. I think the place you'll start to see it is in the underpinnings of the large cloud guys. They'll start to make twists that direction.
Well, and that makes a lot of sense, because I think we see a lot of stuff start there and sort of trickle down to the enterprise. So those are interesting predictions, man. We'll see how it all plays out. But I think my sense is that this is just constantly growing. So you're in a good place. So Ryan, I just want to say thanks so much for coming on. This was really fascinating stuff. I mean, it's always cool to talk about really bleeding edge sort of technologies, and you're obviously a guy who's been there and done it a few times. So really appreciate you sharing that expertise with us. Thanks so much for being on.
Yeah. No, thanks for the invite. I appreciate it. It's been a lot of fun.
Awesome. Thanks for watching. I'd love to hear from you in the comments. And if you like what you saw, please give us a like and think about subscribing. And I will see you in the next video.